This is eHobbyist blog, a log of electronics hobbyist activities aimed at city dwellers who have limited space, limited money, and limited time. My name is Neil. Welcome. During this video, we'll troubleshoot the breadboarded power supply. We will attempt to identify and correct the problem and continue development of the circuit. When I first encountered the problem of not being able to adjust the voltage of this circuit below 5 volts, my immediate inclination was to suspect that I screwed up the breadboarding in some way. And I was actually hoping for this because it's the easiest thing to deal with, although it's time-consuming. What I did was to compare point by point, node by node, connection by connection, every point on the circuit diagram, and compare that to the breadboard. It needs to be done slowly and deliberately because when you're looking at a breadboard, you tend to see what you want to see and not what's really there. Color coding helps. I spent, well over an hour doing this comparison, of which I'm going to be showing about 3 minutes. We'll start off with the 723 IC, and we have power connections. Red power connection is going to the V plus of 723, black to the V minus. Then I've got a compensation capacitor going from a compensation pin to the inverted input. I've got a voltage divider dividing Vref by some proportion, and that's what the non-inverting input is going to see. Then we have the adjustable pot, the voltage divider that is dividing the output voltage and feeding it to the inverting input as kicked up by R3. Q2. And a bias resistor for Q2. And R9, whose purpose is to keep the output zener working. And next I've got the current switching transistor, which is going to restrict the current as seen through R8. Then we have the output from Q1, the power output. So this is a slow point-by-point comparison of the circuit diagram to the breadboard, and after completing this comparison, I was convinced that the breadboard was an accurate model of the circuit diagram. But as I was looking at the circuit diagram, a question cropped up in my so-called mind, and that is, how does the output capacitor C3, which is a 100 microfarad capacitor, discharge? Well, it can only discharge, as far as I can see, through the resistors R4 and 5 and the pot R3. And what we've got there is a total of roughly 70K. Now, 70K discharging a 100 microfarad capacitor from a voltage that went as high as 20 volts, 22 volts. And that can take quite some time, well over half a minute. How is the lack of discharge affecting the circuit? And how does the circuit get adjusted downwards given this slow discharge? So I decided I was going to see what happened when I slapped a resistor across the output, speeding up the discharge of C3. And I was looking for a high wattage resistor, but the one I chose was like overkill. A 7-watt resistor, 1.2K. And I just happened to choose something that was almost right on in terms of the proper value, because once I slapped this resistor on, I began to get viable results. The only conclusion I could come to was that the circuit as published does not work. You have to have a load on it. So with my humongous 7-watt 1.2K resistor, I turn the power on and it's in the maximum position, and I just want to check the input power, and inputting at 28.08 volts. And do some more voltage checking before I start looking at what I really want to look at, which is the output of the circuit. And I've got it at 117 millivolts in the lowest position. And I can increase the adjustment 4.43 volts, coming up to 816. And it is indeed adjustable, is what I'm trying to establish. And once adjustable, it adjusts quickly, and it is stable. The only problem I have with the stability is when you adjust it downwards and in the lowest position of the pot, and it's taking a while to quiesce. And with 1.2K across the output, I'm getting 118 millivolts or thereabouts. Can adjust it upwards. The response is fairly fast and roughly mid-range. I want to see 15 volts, which is common. Okay, it's fairly stable once it settles down as an adjustment. Then the adjustment upwards is pretty quick. Now I've shut the power off and we're waiting for it to get to sub-millivolt range. I have no patience. Turn the bleeping thing back on again, and I'm getting 118, 117 millivolts in the pot adjusted in its lowest position. And what I've done is disconnect this 1.2K load resistor. And I want to confirm that I'm getting the kind of wacko behavior that I did last week. 1.9, 0.8, 0.1? 0.5, it's bouncing. It's really unclear what it's doing. It seems to be going up and down, maybe as a slow oscillation. I don't know. And again, confirming that this resistor across the output has been disconnected. We're going to get it down to zero eventually. Turn the power back on. With the power on, now I should be getting sub-volt readings, and instead it seems to be winding up. Yeah, this is essentially the behavior I saw last week. I'm guessing it's going to go up to 5 point something and stay there, and will never adjust lower with the power on. Or at least never within a reasonable period of time. And here it is. It seems to be stabilizing around 5.2. No load resistor. Now I've got a load resistor connected. This is a 1K resistor, and in its lowest adjustment on the pot, it goes down to 104 millivolts, 0.8. This is fine. I'm not looking for some sort of holy grail of 0.000. 100 millivolts, a tenth of a volt is fine if I can get it down there. What I'm really looking for is a way to test circuits designed for battery operation, and I want to see what happens when the battery runs down. So in terms of low voltage, I would be quite happy with anything that goes down to around 0.8. But this exceeds that. It just goes down to 103, 104 millivolts. So now I just want to check to make sure that this is still an adjustable power supply. The adjustment is relatively quick. Let's see if I can get a stable 5 volts out of this. And tweak here. All right, 4.99, and it seems fairly stable, at least as far as my DVM is concerned. Now I turn the power off. and watch it go down. This is responding much more quickly because it's got 1K resistor to discharge through. And wait to see what happens when it gets below 1 millivolt. You can do it, you can do it. There you go. Let's turn the power back on. It should return to 4.99. And it does. Okay, so I'm beginning to get some degree of confidence that with a 1K resistor slapped across the load, this circuit that does in fact work, and it gets close enough to 0. I mean, 0.1 is close enough. And its lowest adjustment, it's now stabilizing at 104. Now I want to make some changes to the circuit. There's my 1K 1 watt resistor. I've got 2 more capacitors in parallel with the C3 100 microfarad capacitor. What I'm trying to do here is insulate the 723 from rapid changes in load. And the input, I'm doing something similar. We have a diode and 3 capacitors of smaller values aimed at preventing the IC from following load transmitted across these transistors as the transistors try to respond to quick moving variations in load. We don't want to see this reflected in the V plus of the 723, because if it does, it will oscillate. And then finally, the revision I want to put in here is to add variable current limit to the limiting resistor so that in series with a 0.62 ohm limit that will limit it to 1 amp, I'm going to put a 50 ohm variable resistor in. That will give me, at least theoretically, adjustability. In this video, I checked the breadboarded circuit against the circuit diagram. The breadboarded circuit was correct. I identified a deficiency in the circuit as published and corrected it. I was able to adjust the output voltage down to 0.1 volts. I designed some simple modifications aimed at lowering ripple, at reducing sensitivity to high-frequency load variations, and allowing adjustment in current limiting. In the next video, we will continue modification and enhancement of the circuit. If you like this video and the idea of the channel, click on the YouTube thumbs up icon. If you want to be notified as to when the next video is available, click on the YouTube subscribe button. If you want to suggest future directions or topics, make corrections to published videos, or voice your opinion on related matters, then leave a YouTube comment. If you want to see supplementary material that cannot be easily presented in video form, such as high-res graphics, files in different formats, lists of references, go to the corresponding website. Until the next time, good day.